Hey class, welcome to part 2 of 5.3, where we're going to continue our work with kinetic energy. Specifically today we're going to talk about something called the work kinetic energy theorem. And it's this idea that if I do net work on a system, it's going to start to accelerate and speed up, which we know net work requires a net force, which thinking back to Newton's second law would tell us that we have an acceleration. So net work means that I'm going to accelerate and start speeding up, increasing my kinetic energy. Specifically, the work kinetic energy theorem says this: the net work done on a system is equal to the change in kinetic energy of that system. So we have two equations here. So we have the work kinetic energy theorem stated here as net work is equal to the change in kinetic energy. That then expands out to net work times distance times cosine theta. That's net work is equal to the final kinetic energy minus the initial kinetic energy. So what we're going to do today is we're going to look at an example of, we're going to push a box a certain distance. It's going to start with a velocity, and we're going to try and figure out, well, how much velocity does it have at the end using our work kinetic energy theorem. And then in your worksheet, you're going to actually prove work kinetic energy theorem by working out some problems. So again, we're going to look at a box here. We're going to take our world famous box that is going to be 5 kilograms in mass. We're going to push that box a total distance of 20 meters. We're going to push with a force of 100 newtons. We're going to have a frictional force here of 30 newtons, and then we're going to have gravity, which is mg, so 50 newtons. And then we're going to have an upward normal force, because those are equal. We're on a flat surface here. Is going to also be equal to 50 newtons. So we set up our system here. And again, I want to try and figure out, hey, what is the net work in order to figure out the final velocity here? Let's go ahead and give it an initial velocity. So it's going to start moving at 2 meters per second. And when my box reaches the end of my 20 meters, I should put that at the end of my marker there. So let's go ahead. So here, how fast is it moving here at the end of the 20 meters? Well, yeah, we're going to use our work kinetic energy theorem. So let's try and figure out the net work. Let's figure out the initial kinetic energy, and then we'll bring out our equation. So let's start with the net work acting on the object, which we know is net force times distance times cosine theta. Well, when adding up my net force, I have to think, so these two cancel each other out and equal 0. So then I have 100 pointed forward and 30 pointed backward. So I'm actually going to end up with 100 minus that 30, which gives me 70 newtons to the right of net force. So there's 70 there. And goes a total distance of 20 meters. And then what's my angle? Well, we have to think, net force is pointed right, distance is pointed right, so it's going to be cosine of 0, which is going to end up equaling 1. So 70 times 20 is going to give me a whopping 1,400 joules of work on my system. Okay, let's figure out the kinetic energy at the start. Well, that's going to be 1/2 mass times velocity initial squared. So we have 1/2 times the mass of 5 times the velocity of 2 squared, which is going to end up giving us a whopping 10 joules of energy here. So we now have our initial kinetic energy. Well, if we look at our work kinetic energy theorem, meaning that net work is equal to that change in kinetic energy, or the net work is equal to K final minus K initial. In order to solve here, I can add my initial velocity or initial kinetic to both sides, and that's going to get me that the final kinetic energy is equal to the net work plus the initial kinetic energy. Well, as I think about that, what is it telling me then? It's telling me that I add those two together and I get the final kinetic energy. So that's going to be 1,400 plus 10 So my final kinetic energy is 1,410 joules. Well, that is going to be equal to 1/2 times the mass times the final velocity squared, because it's that final kinetic energy. So I've added that energy into the system. The object has decided to speed up. So since it's speeding up, I'm going to drag this down. I'm going to 1410 is equal to 1/2 times the mass, which is 5, times that V final squared. Multiply both sides by 2 and divide by 5. So the 2 cancels out that, the 5 cancels there. That's going to get me that the final velocity is equal to velocity squared is equal to 564. Take the square root of both sides. I'm going to take the square root of my answer. And that gets me the final velocity, 23.75 meters per second. So my object really got speeding up with that net force. Small object, larger net force, that would make sense that happens over a pretty long distance. Now, when you go to the worksheet for the last 2, 9, and 10, what you're going to end up seeing is that you need to, you're going to work this out a little bit more strategically. You're going to calculate each work done. You're going to find the force of friction. So you got to follow the instructions there, but it walks you through step by step, and you're going to prove that this holds true for work kinetic energy theorem. So thank you. If you have questions, come ask me in class. And hey guys, don't forget to be awesome.